Hello everyone, my name is Aditya K. Kamath, and today I will be presenting GPM, leveraging persistent memory from a GPU. Let me start off with a brief summary of what we will be covering in this talk. Currently, the use of persistent memory is restricted to CPUs. Our work helps enable GPUs to harness persistent memory without needing any new hardware. We demonstrate three classes of GPU applications that could benefit from the use of persistent memory. In addition, we create a GPU runtime to help make writing recoverable kernels easier. Non-volatile memories, or NVMs, promise to blur the long-held distinction between storage and memory. Intel Optane is the first commercially available form of NVM. They offer byte addressability and fine-grained persistence at near DRAM performance. In this talk, we will refer to byte-addressable NVM as persistent memory, or PM. Years of research on persistent memory has enabled a large collection of applications that can benefit from it. These include applications like persistent key-value stores and data analytics, among many others. GPUs are a key compute platform today, but are still deprived of direct access to persistent memory. In our work, we address this by enabling fine-grained in-kernel persistence from GPU kernels. An important question is whether there are any applications that can benefit from both the fine-grained persistence of PM and parallelism of GPUs. We find that there are many such applications. Consider persistent key-value stores, or PKVS, which are the backbone of large-scale social network sites and search engines. These applications rely on persistence for fault tolerance. A significant amount of research revolves around improving the performance of persistent key-value stores. On the other hand, researchers have used GPUs to increase the throughput of get and put operations on regular key-value stores. Enabling in-kernel GPU persistence allows us to bring these two together, allowing applications to benefit from both the persistence of PM and the parallelism of GPUs. We allow GPUs to accelerate persistent KVS for the first time and refer to it as GPU Accelerated Persistent KVS, or GPKVS. Now the question is, what does GPKVS provide over existing PKVS? We find that GPKVS outperforms both commercial PM-optimized state-of-the-art PKVS like RocksDB and Intel PMEM-KV, as well as academic PKVS like Matrix-KV by multiple folds. We achieve this speedup while providing the same persistent guarantees as the CPU-based counterparts. Now we will take a look at what we do today on a system that has both Optane NVM and a GPU. Today, even on a system sporting both a GPU and persistent memory, a GPU kernel does not persist the result of its computation directly on the PM. Instead, it relies on the CPU to do so. We call such a system CPU-assisted persistence, or CAP. Take the example of GPKVS. The GPU performs batch set operations. It then transfers the entire key-value store to the CPU to guarantee persistence. Persistence is guaranteed by the CPU flushing and draining data from the caches. This is needed to ensure recoverability in the presence of volatile caches. However, this system exhibits unnecessary data movement and serialization by the CPU while guaranteeing persistence. To overcome this, our goal is to expose PM directly to GPU kernels and enable in-kernel GPU persistence. This will allow GPU kernels to directly persist results of their computation without needing CPU assistance. For an application like GPKVS, the GPU is able to perform both the batched set operation and guarantee persistence without relying on the CPU. In-kernel persistence provides several benefits. First, it eases programmability, as programmers do not have to split the GPU kernel whenever persistence is needed, and can embed the logic for persisting data in the GPU kernel itself. Second, by relying on the CPU to persist the results of the GPU's computation, we lose the benefit of the GPU's massive parallelism when persisting results. To demonstrate this, we create a micro benchmark that writes and persists 1 GB of data from the GPU to the persistent memory. We vary the number of CPU and GPU threads persisting these results, and find that where multiple CPU threads could only provide 1.47x speedup over single-threaded CAP, GPUs can speed it up by up to 4x. Hence, in-kernel persistence can significantly optimize data persistence from a GPU. We also note that there are several applications in which the GPU only updates a small portion of the data, but this portion is not known until the computation on the GPU is performed. Consider the case of GPKVS, where only a few key value pairs of a large persistent key value store may be updated. Under CAP, we will have to move the entire key value store to the CPU, since the CPU is not aware of which pairs were updated. The GPU then relies on the CPU to persist these results. By allowing in-kernel persistence, we can move and persist only the key value pairs that are updated, hence reducing extraneous data movement. Direct access to PM allows a GPU application to perform in-place updates through load store operations on the PM resident data structures, reducing the cost of updates and data movement to the PM. Towards this, we make three key contributions. We create GPU with persistent memory, or GPM, purely in software without any new hardware support. We create a benchmark suite, GPMBench, with three categories of applications that can leverage both GPU parallelism and PM persistence. And we create a CUDA runtime library, LibGPM, optimized for GPUs that allows a GPU program to easily leverage fine-grained persistence. We will first discuss how we conjure GPM. To understand the internals better, we'll make use of a schematic model of our system. Note that currently no GPU hardware exists with onboard NVM. Instead, the NVM is attached to the CPU and is accessed over the PCIe bus. We refer to the CPU side DRAM and NVM as host memory and the GPU's GDDR as device memory. We will now take a look at the three steps needed to create GPM. First, we map parts of the NVM to the GPU's address space through NVIDIA's Unified Virtual Address Space to allow GPUs direct access to PM via load store instructions. Unlike CPUs, today's GPUs are not designed for use with PM and do not have instructions to flush individual cache lines. However, system scope fences, originally designed for synchronization, flush data to system memory. The host memory is a part of the system memory, and so the fence can be used to flush writes from the GPU to the NVM in the host memory to guarantee persistence. However, a system scope thread fence is not sufficient to guarantee persistence. This is due to a seemingly unrelated feature on Intel servers called Data Direct I/O or DDIO, which stops writes from immediately reaching the memory. DDIO was originally designed to improve the DMA access latency of devices. When enabled, writes to the CPU memory from I/O devices like network interface cards, GPUs, are cached in the CPU's last level cache. This means for GPM, the fence completes as soon as the writes reach the CPU's volatile LLC and not the persistent memory. Hence, whenever a persistence guarantee is needed from the GPU, we selectively turn off DDIO, which ensures that the thread fence completes only when the GPU's writes reach the NVM, thus guaranteeing persistence. In summary, we build GPM, which enables GPU kernels to perform in-place updates to PM data structures and also guarantee persistence wherever the program semantics demand by 1. Mapping parts of NVM to the GPU's virtual address space using UVA, 2. Ordering writes to PM using system scope thread fence, and 3. Guaranteeing persistence by selectively disabling DDIO. An important aspect to consider is what applications can make use of a system like GPM. For this, we create a benchmark suite, GPMBench. We categorize applications that benefit from in-kernel persistence into three main categories. The first category is transactional applications like GPKVS, which we have already discussed. Other applications in this category include GPU-accelerated persistent databases. For these applications, the entire data structure, for example the KVS or database, resides on the persistent memory, and transactions are used for crash-consistent updates. The next category consists of long-running applications like DNN training, which may run for days, which are iterative in nature. Other applications in this class are scientific computations like computational fluid dynamics. These applications checkpoint their data regularly to avoid significant recompute following a crash or premature termination. We finally enable a new class of workloads called native that perform fine-grained in-place updates to PM resident data structures. These include graph processing applications operating on large PM resident graphs. These three classes of applications require three types of persistency support. Transactional applications require logging, while long-running iterative applications need an easy way to perform checkpointing. Native applications need a basic ability to persist data at a fine grain. We'll now look at how we provide this persistency support through our runtime library LibGPM. We create a detailed set of API which extracts complex logic for persistence from GPU programmers. You don't need to read the table as the full details are in the paper. These API are split into 3 different categories, reflecting the categories of applications mentioned previously. Our library provides GPU and NVM optimized interfaces for logging, checkpointing, and persistency primitives. Due to this, the amount of code changes needed in the GPU kernel to leverage persistent memory is low. The interface also encapsulates many GPU optimized innovations. In this talk, we focus on GPU optimized logging, but the rest can be found in the paper. The cornerstone of LibGPM is GPU optimized write-ahead logging. We will first discuss how logging is conventionally performed in multi-threaded applications. The most basic approach is to have a single log file and a single lock guarding it. Different threads that wish to perform write-ahead logging need to take the lock before inserting data. This approach doesn't scale well as it creates serialization among potentially thousands of threads that perform logging. To optimize logging for multi-threaded applications, sharded multiple logs are used, where each thread can write to their own private shard of the log without needing locks. While this works well for multi-core applications, it doesn't scale well for the GPU's architecture consisting of thousands of concurrent threads arranged in a hierarchy. We instead propose a GPU-optimized logging that reflects the GPU's thread hierarchy in the log structure. Each grid shares a single log that all threads in the grid write to. The log is distributed among the thread hierarchy, providing a unique offset in the log where threads can insert data. For example, each thread block has a unique offset within the log where they can insert data. Similarly, within this offset, each warp has a unique offset where it can insert data. In this way, the hierarchy of the GPU threads is reflected in the log, and data is inserted into the log without any locks. We will now look at how threads within a warp insert data. Our second innovation is that we take advantage of GPU's hardware coalescing. Cache lines in GPUs are typically 128 bytes long, and each warp contains 32 threads. We split data being inserted into the log into 4-byte chunks. These 4-byte chunks are then written into the log in parallel by all 32 threads within a warp. This allows the GPU hardware to coalesce the writes into a single 128-byte parallel write operation. HCL makes use of 2 properties that allow it to bring significant performance benefit. First, as each thread has a unique position in the log to insert its data, it removes the need for locks. Second, it uses 128-byte writes to take advantage of hardware coalescing. On a micro benchmark, we found that HCL scales well with an increase in the number of threads compared to using a distributed log. On the x-axis, we are increasing the number of threads, while the y-axis shows latency, where lower is better. The orange line shows distributed logging, while the blue line shows HCL. HCL provides around 3x speedup over conventional logging. We shall now look at our experimental platform and the results that we obtained. This table shows the details of our evaluation platform. This platform uses real hardware available on the market today. Notably, we use Intel Xeon CPUs with Intel Optane and an NVIDIA Titan RTX GPU. These are the specific applications contained in GPMBench, divided into 3 categories. In total, we performed our evaluations on 9 applications across these 3 categories. Our baseline is CAP, where data is transferred in bulk from the GPU to the CPU and then persisted. For applications like GPKVS and GPDB, the speedup mainly arises from the reduced amount of data that needs to be persisted. For example, only individual key-value pairs need to be persisted instead of the entire KVS. BFS speeds up for a similar reason, as in each iteration only a sparse set of updated visited nodes need to be persisted instead of the entire vertex list. Checkpointing workloads would benefit from direct access to PM, removing expensive data movement through the CPU. GPM is not only beneficial for applications on today's platform, but also holds significant promise for upcoming e-ADR feature. e-ADR stands for Extended ADR and extends the power fail protected domain to also include the caches. What this basically means is that data is guaranteed to be persisted as soon as it reaches the caches. For CAP systems, e-ADR eliminates the need to flush caches. However, the CPU still needs a fence instruction to order the data and guarantee persistence. For GPM, DDIO remains enabled even when persistence is required, and a thread fence operation can complete as soon as the data reaches the CPU's LLC. We now show the benefits of e-ADR for both CAP and GPM. CAP systems see limited benefits with e-ADR. This is because although e-ADR eliminates the need for flushing data from the CPU, most of the time in CAP is spent in transferring data from the GPU to the CPU and not in persisting the data. For GPM, the applications which frequently persist their data, for example those due to logging, benefit the most since fences complete as soon as data reaches the LLC. In contrast, checkpointing requires a single persist after writing the entire checkpoint, and thus it is mostly agnostic to e-ADR. We observe that GPM with e-ADR is 24 times faster than CAP with e-ADR on average. This is because GPM's advantage of leveraging GPU parallelism in writing to PM and avoiding extraneous data movement is unaffected by e-ADR. At the same time, the fact that e-ADR allows GPM to guarantee persistence even with DDIO enabled improves the performance significantly. Please see the paper for a full evaluation. To summarize, we find that GPUs can make use of the persistence that NVMs provide. Towards this, we propose GPM to allow GPUs to leverage the persistence offered by PM. Our contributions include creating GPM with in-kernel fine-grained persistence in current hardware, showing the importance of PM for GPU apps with the benchmark suite GPMBench, and building a GPU runtime, LibGPM, allowing programmers to easily use GPM. Our artifact is open source and has received all 3 badges for evaluation. Thank you.